All right, we're here for the AP Physics Pulleys worksheet. Taking a look at the first one, it says an inventive child named Pat wants to reach an apple in a tree without climbing the tree. Sitting in the chair attached to the rope. So here, we'll go ahead and draw Pat in here. So here's Pat, right? Sitting on the chair. Okay. And it says she's sitting in the chair that's connected to a rope that passes over this pulley. Okay, that's frictionless, and we'll assume the mass is really small. Pat pulls on the loose end of the rope. So here we go. So she's grabbing the end of the rope there, right? He or she. Here we go. With a force such that the spring scale here reads 250 newtons, which tells us that that's the tension in the rope, okay, that passes over the pulley. Pat's weight is 320 newtons, and the chair weighs 160 newtons. Draw free body diagrams for Pat and the chair considered as separate systems, and then one for Pat and the chair together considered as one system. So let's go ahead and give that a shot. So let's say together, okay, I'm sorry, separate systems first. So we'll say, okay, let's see here. Here is Pat. Okay, and I'm gonna represent Pat like this. There's Pat's arm. Okay, I'm gonna simplify. There we go. Simplified diagram. There's Pat. Okay, and then we'll say the chair. All right, and we'll say, okay, the chair. There's that chair that she's sitting on, or he's sitting on. Okay, then we'll do forces. Okay, and so you say, well, starting with Pat, you say ranged forces. Of course, there's going to be gravitational force. This would be the mass of Pat times G. Okay, contact force is what's touching Pat. And you realize there's two things touching Pat. There's the chair and there's the rope that she's hanging on to. So, so you say, well, the chair, are they being pressed together? Yes, gravity is pushing her into the chair. So the gravitational force, so there's a normal force. I might label that normal on Pat by the chair. Okay, and then her hand here, right, is pulling on that rope, and so the rope is pulling up on Pat's hand. So that'd be a tension. Okay, and now we say, well, with the chair, you say range forces is gravitational force, mass of the chair times G. Contact forces, the chair is being touched. Now, I'm going to go ahead and treat these ropes like it's just like one rope. Is that okay if I treat all this as part of the chair? So there is one tension pulling up, I'm going to say, if that's okay with you, right? So like I'm kind of doing the chair and all this is my system. You know what I mean? Okay. I mean, this looks like it's some vertical bars or whatever. And anyway, we'll just treat all that. And then you say, and then there's the other thing touching the chair besides this rope is Pat. Okay. And so there'll be a normal force down on the chair by Pat, right? Pat pushes, the chair pushes up on Pat, Pat pushes down on the chair. Okay. So that's the force diagram for the chair. And then we can do a combined system for Pat and the chair. So, you know, Pat, right, and the chair together. Good enough, right? Okay. And you'll say, oops, there we go. You'll say, okay, what outside forces are acting? And you'd say, well, ranged forces. Do you want to do two gravitational forces, one on Pat, one on the chair, or one combined? I don't know. We'll do one combined. So this would be the mass of Pat plus the mass of the chair times G. And then we'll have the tension pulling up on the chair and the tension pulling up on Pat's hand. Okay, and that's my force diagram for the combined system. And you see, if I go ahead and I compare these diagrams to this one, you can see that I went ahead and combined these two gravitational forces into one arrow. Okay, and I've got my two tensions, tension, tension. And you see what's missing is the normal forces. And you see that makes sense because this normal on Pat by the chair and the normal on the chair by Pat, those are equal and opposite. If I put them on the same diagram, they would just cancel out anyway. You don't include forces that are acting between the parts of the system. Okay, so there we go. So that is our combined force diagram. So that's part A. Okay, part B says, show the accelerations upward and find its magnitude. So I'm going to go ahead and do most important formula in physics. I'm going to do sigma F equals ma. I'm going to do that. Let's see. Let's do that for the combined system. Okay. So if I go ahead and so I'm going to use the purple system for this. And I'm going to do a sigma F equals MA, right? And so you say I'm going to do forces up minus forces down. And so I'm going to say, hey, I've got two tensions pulling up minus MP plus MC times G, that gravitational force equals mass. Now, my system is the combined system. So on the right side, that mass needs to be the mass of Pat plus the mass of the chair, right? Times A. Okay, now, which of these values do I know? And you say, well, I do know the tension. They told me that the scale reads 250, so that's 250 newtons. Do I know the masses? Well, they didn't tell me the masses. They told me the weights. So I'm going to have to make use of the fact that a gravitational force, right, is, again, mass times G. So the weight is M times G. So to get mass, I'm just going to have to do that gravitational force divided by G to get the masses that I want. So where it says mass, so here we go. So I'm going to do 2 times 250 newtons for my tension minus, now when it says mass, I'm going to have to put in, well, this is M times G. That would be the weight. And the weight is just going to be that 250 plus the 320. I'm sorry, 320 plus the 160. Sorry, the mass of Pat, the weight, combined weight. So I'm distributing the G and doing the MGs. Anyway, you get it. So it's 320 plus 160. All right, so that's the combined weight. But over here, I need just the mass. And so here, I'm going to get the mass by taking that weight and dividing by G. So over here, that would be the weight divided by G. So that's going to be that 320 plus the 160, and I'm going to divide by 9.8. And so then I'll have that times the acceleration. And so now I have an equation that only has one unknown, the acceleration. And so now I can just go ahead and do my algebra and rearrange. And when I do that, I in fact get a value of 0.408 meters per second squared for acceleration. And I get a positive value, which tells me that the motion is upward in the positive direction. So that's part B. So now do part C. In part C, they want us to find the force between Pat and the chair. And so you say the force Pat exerts on the chair. So so that force, of course, that normal force between them, it doesn't show up on the combined system. So now I'm going to have to use one of these diagrams. I'm going to choose to use the chair, find the force. And I mean, I could use Pat and then just that NPC is the same as NCP, but let's go ahead and do the chair. So for the chair system, all right, we're just going to do a sigma F equals MA. And so then means we're going to have T minus NCP, and that's, of course, what we want to find, that normal force, minus the weight of the chair. And that's going to be equal to MA. And again, because our system is just the chair, this will be just the mass of the chair on the right side of F equals MA. All right. Now, at this point, you'd say, well, the tension we know is 250. This is what we're trying to find. We know the combined here, we know the weight of the chair is 160 newtons. The mass of the chair, we're going to have to, again, take the weight divided by G to get the mass. And then acceleration we just solved for over here. So we know everything in this line except for the normal. So rearranging once real quick, NCP is going to equal, let's see here, I'm going to move this stuff over and flip the signs. So I'm going to end up with T minus MCG minus MCA. All right, so I'm going to end up with, because when I move to the other side, the signs flip, but then I'm going to multiply all of by -1 to make that positive. So anyway, that's what we end up with. And you say, hey, we know the values here for these things. We know the tension is 250. We know the weight of the chair is 160. The mass of the chair is going to be the weight divided by 9.8, weight divided by G. And the acceleration we just got was 0.408. I'm going to put another digit on there. It's in my calculator. It goes to 3. And when I do the calculation, I came up with that normal force to be 83 1/3 newtons. I was keeping all the digits in my calculator. It came out to be a nice round 83 1/3 newtons. And so that's it. That's that problem. So what's interesting about this problem to me is the way that Pat is interacting with both sides of the pulley. So I just kind of did force diagrams for Pat. I'm not doing, usually when we have pulley problems, we have separate objects and they're moving along as this goes, this mass over here goes up, this mass over here goes down. And so we pick one direction along the rope or whatever, you know what I mean? Or as this goes up, that goes down. But in this case, we're just analyzing the one side, really like the one side of the pulley basically. And so I just, one direction is up and down. Okay, the stuff we're analyzing is on the same side. So I just have one direction up for everything. Okay, and that's that problem. Okay, so now we take a look at the second pulley problem. Okay, so this is a pulley system. Okay, so we have this one upper pulley, and that's in this rope here is like attached to the framework, the shackle that holds the pulley. And this rope here is attached again to the framework, the shackle that holds the pulley. And like the axle of the pulley kind of spins in it, in that shackle, in that framing. Okay, so these ropes are, if it was a ship, they'd be called the standing rigging. And this here is one rope that wraps around the upper pulley and then down and around the lower pulley. And then here it attaches to the shackle, okay, to that. So this part of the rigging that's going to be, the rope that's going to be moving on a ship would be called the running rigging, these ropes that move, that aren't just holding things steady. Okay, and so the point of this is, if you yank down, if I was to pull harder on this rope, then that would kind of pull up on this rope and it would shorten this, and the pulley would lift up, the little lower pulley would lift up, and that would lift up this mass. Right, and that's kind of the point. But in this case, we're just holding everything steady. Nothing is moving, so everything's in equilibrium. All right, and that's going to let me crank through this pretty quickly. So what we want to do here is we've got 5 tensions. Okay, the tension in the rope here, the tension in the standing rope here, the tension in the main rope here, this standing ring here, and this tension in the main rope here. So I'm going to go ahead and I want to solve for the sizes of these 5 tensions. Okay, and I'm actually going to do it twice. Okay, I'm going to, this isn't clear. I should change this and say, find the tension, the 5 tensions in terms of M and G, and find the 5 tensions in terms of F. Okay, as 2 separate things. Okay, we don't need to have all 3 variables involved. And then find the magnitude of F in terms of M and G. It'll be easy once we got that. Okay, so here we go. So that's what we're going to do. So to do this, of course, we're just using sigma F equals MA, right? And we have to choose a system, right, to analyze, right, or multiple systems. You see, I've got 5 variables here, right? So like technically 5 unknowns, I really kind of need 5 equations basically to work with. Well, the first realization here is that if I assume that these pulleys are really lightweight, I know they don't look like it in the picture. We're going to assume that they're very lightweight compared to the mass of the thing you're raising here. All right, these are very lightweight, massless, frictionless pulleys. Okay, let's call this massless, frictionless pulleys. Okay, dunk, 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 dunk. And we know that we don't mean they really have no mass or friction. We mean it's just small enough that we can ignore it. Okay, and so let's choose our system. So what first realization I was going to say is that this is one rope wrapping around here, and so we are going to say, again with massless frictionless pulleys, that this is the same tension all the way through. So we could right away say, hey, T1 equals T3 equals T2, okay? Because it's the same rope all the way through. The other thing is, if this is being held steady, isn't it true that this tension pulling up is going to be balanced by this F pulling down? So that actually all just equals F too, all right? So now let's talk about T4 and T5 are the other tensions we need. So I'm going to go ahead and use as a system. Let's look at that. Let's look at that hanging mass. Okay. Okay. If I want to start getting like M's and G's in my equation, so I'm going to do a system like this. Okay. So my system here is just the hanging block. Okay. So now if I do a sigma F equals MA for that, I'm going to say, I'm going to call up, down, up positive, down negative. Forces up minus forces down, so that'll be just T5 going up minus a gravitational force mg going down. And the acceleration is 0 because everything's being held steady. All right, so that's going to give me that equation. All right. And let's do another system. Okay. I think for my other system, I'm going to do the lower pulley here. There's different ways I could do this, but I'm going to do the lower pulley. So let's see here. Now, if we're going under the assumption that the mass of the pulley is so small that we can basically ignore it, then I don't have a significant gravitational force to worry about. So I am going to have, though, what else crosses the system boundaries? These 3 ropes. I'm going to have 3 tensions. So when I do my, sigma F equals MA for that guy, it's going to be forces up minus forces down. So I'll have T2 plus T3 minus T5 equals 0. Right? Up, up, down. And so that gives me an equation that relates T5 into these other T's that I already know something about. And then I need to get something about T4. So I could choose to do the upper pulley or like combination of the 2 pulleys together, or I'm going to go ahead, I'm going to do the system, I'm just going to do it big. I'm going to say that my system here is now I want to cut through here, right? Because I need to have that tension show up, T4 show up in my calculation. So it has to be a force from outside the system. So I'm going to cut my system boundary there. And I'm going to go down and look. I'm going to include all of this. And I'm going to kind of cut through here. Does that make sense? So, or actually, you know what? Let's make life easy. Let's do this. Okay. So basically, I'm just going to have this outside F yanking on my system. I'm going to call all the ropes, all the pulleys in the back block, all one big system except for this rope. Okay. So if I do this, this is a great big combined system. It's basically the whole pulley system, and the block, right? Then I'm just going to have this tension pulling up here, T4, when I do my sigma F as MA. T4 going up, and I'm going to have this force here and gravity pulling down. So T4 minus F minus mg. And of course, we're not accelerating anywhere, so that's going to add to 0. So there we go. So now I have technically, I think this counts as 3 separate equations, right? 3 independent equations. F is T1, T1 is T2, T2 is T3. It's 3 independent equations. The other ones can be made by combinations. Anyway, and then here is an equation, and here's an equation. I've got tons of equations to work with here. So now it's just time to do some algebra. So I think what I want to do is, do you want to find everything in terms of F first or everything in terms of mg? Let's go ahead and do everything in terms of mg first. Why not? Okay, so finding the 5 tensions in terms of mg. Well, first off, T5 minus mg is 0. So right away we can say, hey, T5 equals mg. Okay, so that's one down. 4 more tensions to go. When I look at the lower pulley, do you see that I'm going to have T2 and T3 equals T5? Right? So looking at this one, I'm going to have T3 and T2 is T5. Well, T2 and T3 are equal to each other. So it's like, if you want, don't think I want to do that equation. I think I wanted to work with another. That's okay. I want to do double T3 if you want, equals T5. Okay. And we know from here that T5 is mg. So 2 times T3, say, would be equal to mg, which means that T3 is mg over 2. And since T3 equals T2 equals T1, so now we have those 3 tensions in terms of mg, right? And T5 in terms of mg. We just need T4 in terms of mg now. So we go to the equation that has T4, and we say, okay, hey, what's T4 going to be? If I rearrange this, you would say T4, so I'm going over here, you say it's going to be equal to F plus mg, and F is the same as T1, and T1 is equal to mg over 2. So this is mg over 2 plus mg. And so you say, okay, T4 is 1.5 or 3/2 mg. So that is all of my 5 tensions in terms of m and g. Okay. Now, could I also find my tensions in terms of F? You say, well, sure, because we know that F is the same as T1, T2, T3. So that's actually the first one. So in orange here, this is five tensions in terms of M and G. Okay, but we can also do those 5 tensions. I'm going to squeeze it in here. Can we do 5 tensions in terms of F? Okay, like I said, I wish I'd broken them up into different questions. So you say in terms of F, we say, well, right away, that's 3 of them down. Okay, we know that T1 and T2 and T3 are just equal to F. So that's those done. I just got to do T4 and T5. Well, over here, we know that, where is it? These guys are mg over 2. And T4 is, and those guys are equal to F, right? So T4 is an F and an mg, but F is mg over 2. So this is like 2F. So this is F and 2F. T4, I don't know if that was clear enough here. Let me jot this down. Okay, but we found from before here, these are equal to F, and these are equal to mg over 2. So F is mg over 2. So mg is twice that, right? F is mg over 2. This is double that. So this is just F and 2F. So that would be 3F. It's T4. So there's T4 in terms of F. And then lastly, T5. T5 is mg, but since mg over 2 is equal to F, you're like, okay, fine, so that's double. So T5 must be 2F. All right. I hope that was okay that I just kind of talked through that instead of going through all the formal algebra. Okay, but that gives us the 5 tensions in terms of F. Okay, and if you think about it, if I look at the big green guy here, right? What's interesting is, and this is kind of the whole point of this whole pulley thing, all right? And this is kind of what I'm going to get with that this next part. Can I have F in terms of mg? And I kind of just talked through it there as we did it, that since F is equal to these T's, and these T's came out to be mg over 2, F is mg over 2. Okay, and that's that final bit. And I was using that in the last part, sorry. But yeah, but we know that F is mg over 2. So that's the whole point. This is like the purpose of pulleys, right? One of the purposes is, even though this block, I'm trying to raise that block. Okay, I'm trying to lift that up. And it has a mass of mg. But because of the pulley system, I get to pull with a force that's just half as big. And I can hold it steady. And if I pull just a little bit harder than half the weight, it'll start to go up. And so it seems at first, kind of like magic, that I'm able to apply a smaller force than this weight and balance out gravity. They're like, what? How does that work? Well, the trick is here, because what I've got going on here is I've got two tensions pulling up to balance out the weight of this. If I did a combined system, I wish I'd done a combined system now, the lower pulley plus M. But you see I've got two ropes pulling up. And so, but the tension I apply here gets applied twice then. Do you see that? How hard I yank here, it actually ends up pulling up twice on this. So it only has to be half the weight of mg. There are compound pulleys, and I will show this in class on next class. I'll set up a compound pulley that where there's a bunch of separate like pulley wheels on one axle and a bunch of separate pulley wheels, and the rope goes around and around and around and around, and you get the same rope yanking up multiple, like a whole bunch of times. I'll set up one that I think I can set up one that has 8 ropes pulling up, and so that means you only have to pull down with 1/8 of the weight to lift something, which is like really cool. And like I said, it seems like cheating the universe somehow that I can pull down with 1/8 the weight and pull up 8 times the mass, but it actually all works out just fine when you look at it in terms of energy. And so I will come back and address this. I'll address it in class. I'll talk about it in class with an example. But it's cool the way it works out. And so it lets you exert less force to lift things, which is really cool. I'm struggling with myself that I want to explain this now, why it's not cheating the universe and how it works out. But I'm going to save that for class. I'm going to save it for class. Okay, so that's it. That's this problem. Like I said, pulleys are cool, how they work. It's just neat. Like I said, you get to like take this one force and you get to like kind of double it, right, effectively, because it pulls, that rope pulls up twice. So neat. So neat. All right. I will see you in class.